Okay. Is this okay? All right. So I mean, there's two things wrong with using this map as sigma. This proposition from yesterday required this thing, this property, which works. The things wrong, of course, are that the source is not what we want, and the target doesn't have HR, and moreover, sigma is not injective. Okay, and we needed sigma to be injective on non-negative degrees. Okay, so there's three things wrong, but all of these will be fixed by replace. So the goal is to replace sigma with the first differential in a minimal Rouquier complex. I'll spell that a little better once I'm not writing at the bottom of the board. And that will be the answer that will fix everything and give us what we need. So for the rest of this time today, I'm going to talk about Rouquier complexes, and then we'll get back to finishing this proof later. So Rouquier complexes. So Rouquier is pretty brilliant guy. He's one of the fathers of categorical representation theory, one of the two inventors of SL2 categorification. Also a Zirkel bimodule expert. And he came up with these complexes as a way to categorify the braid group. And I already showed you kind of what they were in this earlier colloquium lecture, but I'll do it again. These complexes were known for a long time in all sorts of other contexts for Weil groups. And Rouquier was the one who sort of observed, well, this works for arbitrary Coxeter groups, including non-crystallographic ones. So this is a well-known construction in other contexts. Okay? But we've seen two short exact sequences. Okay? We have BS going to R by multiplication by multiplication. Since this is a map of degree 1, I should put a 1 here. So in the rest of this talk, all my maps are going to actually be degree 0 once I keep track of the grading shifts. And it will finally be important. And the kernel of this map was RS shifted by -1. So RS is this thing I defined in the colloquia, right? RS is R as a vector space where the right action shifted by S. So this map sends 1 to CS minus, which is 1/2 of alpha S tensor 1 minus 1 tensor alpha S. And this is another canonical element. This is a canonical element for the dual Frobenius algebra structure. It's not really a Frobenius algebra structure. This is sort of like the Casimir for the pairing R cross R to RS, which instead of taking two things and multiplying them and applying the de Mazur operator, we now take two things and apply S to the second one, and then apply the de Mazur operator. Okay, so this is sort of the dual pairing, and this is a sum of dual bases. Okay. And then we have the other short exact sequence, where R maps into BS, and since this is a degree 1 map, so -1 here. And the kernel of this is isomorphic to RS. And this map here is its multiplication, but again, you can't just multiply. You have to multiply with an S. This is the dual multiplication. And there it is. So we had these two short exact sequences. And what they yield, you should think of these as Zirkel resolutions of these non-Zirkel bimodules. Okay, think of as Zergel resolutions, or projective resolutions of standards. Okay, so I'm going to call this complex where this guy is in homological degree 0, and this guy is in degree -1. I'm going to call this Fs inverse. It's a complex of Zergel bimodules. Okay? And it has a map to this complex here. So this map is a quasi-isomorphism, which is to say that it induces isomorphisms on homology, but it has no inverse. There's no map from RS1 into BS. And there's certainly no map which is an inverse of this one. And similarly, I'm going to call that map BS to R1. I'm going to call this Fs. And of course, this one has a map from Rs minus 1, but it's a quasi-isomorphism with no inverse. So on the Grothendieck group, what are these, right? You can talk about the Grothendieck group of complexes by taking the alternating sum of the objects. So via the usual Euler characteristic map, right, where you take a complex to an alternating sum, the image of Fs inverse is Bs minus R shifted up, which is Hs underscore minus V, which, if you remember the computations, is actually just Hs. Whereas the class of Fs is actually Hs inverse. So I'm choosing Fs to be the one that I care about rather than Fs inverse, just to make things a little nicer. Okay? Really, I should have switched the inverses to really make it match up with the Grothendieck group. But I prefer him. I like him better. Okay, so let's KB of Zergel bimodules denote its homotopy category. Okay, so Zergel bimodules are an additive category, which means you can take complexes of them. That makes sense. Now, there's no homology of these complexes because there's no kernels and no images. Okay, but you can take complexes and you can talk about homotopies and you can mod up by the ideal of homotopies. So this makes sense for even just an additive category. Okay? You can't take its derived category because that talks about quasi-isomorphisms, which depends on homology. So there's no notion of the derived category. The best you can do is take the derived category of R bimodules. Okay? This makes sense for an abelian category. Okay. So do people know what these are? The homotopy categories and the derived categories? Good. Good, good. Okay. So a Ruquier complex associated to an expression, not necessarily reduced, is actually, this is an expression in the braid group. Right? Which is to say that we don't take S squared as 1, so we need SI or SI inverse. Right? S1 plus or minus S2 plus or minus dot, dot, dot. And so this is going to be fs1 plus or minus tensor, fs2 plus or minus tensor, dot, 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 dot. And this is an element of this homotopy category. Okay? So something you have to remember is that when you tensor things, when you tensor complexes, you end up with a total complex, and there are these annoying signs. You have to keep track of sign conventions, and your life is really annoying. Okay? So I'm going to give you just a nice way to keep track of the signs in a Riquier complex in a sec. So I'm going to give you some examples. Well, let's take fs and tensor with fs inverse. Okay, remember, this one is bs goes to r1. This one is r minus 1 goes to bs. So when we tensor them together, we have 4 terms. In degree minus 1, you have the minus 1 and the 0. So you have bs minus 1 in degree minus 1. In degree 0, you have 0, 0, and 1 minus 1. So you have bs, bs, and r tensor r with a shift by 1 minus 1. And then in degree 1, you have bs with a shift by 1. Okay, now what are these maps? Okay, and so take the total complex. So these things are added together. So what are these maps? So remember, this map is this, and this map is that. So what I'm supposed to do, this guy is actually him tensor him. So to get to him tensor him, I apply this map with the identity of that. So I do the identity of him next to that map. Meanwhile, to get to him, I do this map with the identity of that one, which is just actually the vertical dot. Okay? Then over here, I apply the identity of something with the other guy. Did I do this correct? Fs tensor Fs inverse. Yeah, it's a question of which one goes in front. I think maybe I preferred. What did I prefer? It goes to Bs. No, the way that I wrote it is this way. So here I do the identity of him, and then I do that to the first, and then I do that to the first guy. So it's like looks like this. Whereas over here, I do the identity to the other thing. And then in order for this to be a complex, there needs to be a sign somewhere. And my rule for signs, okay, which will work. Okay, so first off, let's figure out what the rules are. So the shifts are equal to the homological degree. Right? That's true here, so it's true when you tensor product. So we kind of don't need to keep track of the shifts. They're easy to remember. That's great. Okay? Another way of saying that is differentials are degree 1 before shifts. Okay? So the second statement is that all maps are a single dot next to some identities. Okay? Or at least all individual arrows. And the third statement is that the sign is -1 to the number of lines before the dot. So this dot has no lines before it, this dot has no lines before it, this dot has no lines before it, this dot has 1 line before it. Okay? This is a sign convention which is technically the sign convention that one should use and will give you a perfectly good complex. However, it's not the sign convention we'll end up using later, but I prefer all these initial maps to have positive sign. But So we'll use another one later, but this is a good one for practice.
Just to make it understand. I mean, whatever is the standard, one standard way of doing science, we work it out, this is what it required.
Yes, this is like this is the way that they tell you in the books to do the signs. Like it has to do with computing the degree of the map, right? You put signs on maps in certain homological degrees. Yeah, and so like yeah, this is technically what you should do. Okay. So now this is supposed to be an action of the braid group. Right? These are supposed to be inverse complexes. So this tensor product complex is supposed to be isomorphic to the identity complex. What's the identity complex? It's R in degree 0. Okay. So these things are supposed to be isomorphic in the homotopy category, which is to say that there's chain maps there and back. Okay? So there has to be some chain map. Okay? Well, what's a chain map? I mean, this goes to 0, this goes to 0. That's clear. You know, there's sort of a one-dimensional space of degree 0 maps here. Okay? So BSBS goes by some multiple of the cap, and R goes by some multiple of the identity. Well, I'll write 1R just to be clear. And there has to be some chain map back, right, which is, again, some multiple of this and some multiple of the identity, C and D. Some relation between A and B has to be satisfied in order for this 0 to be the same as this. Okay? And similarly, some relation between these. And then some relation between these come by the fact that when you compose these, here and back, you have to get the identity of R. Because there's no homotopies in this complex that you can construct. All right, well, when you compose there and back, you get an empty circle plus this multiple of the identity. Empty circle is 0, so you know B times D is 1. And then when you compose here and back, that's not going to be the identity of this complex, obviously, because it's 0 here and it's 0 there. But it's supposed to be homotopic to the identity of this complex. Okay, you then need to construct a homotopy. So you need maps of degree -1. Maps of degree 0 when you have the shifts. But after you ignore the shifts, they're maps of degree -1. So there's no map of degree -1 from R to BS, but there is a map of degree -1 here. And there is a map of degree -1 here. You know, with some scalars. Okay? And you're going to use these to build a homotopy between the composition and the identity. Okay, so this is an exercise. Homotopy equivalent. Okay, great. This is a great example. Let me give another example down here in the corner. What happens if we just do FSFS? Okay, and here's why it's the braid group and not the Coxeter group. So in degree 0, you're going to have BSBS. In degree 1, you're going to have 2 different copies of BS, 1. And then degree 2, you're going to have R with a shift by 2. So it's easy to guess what these maps are now. This must be the dot. The dot. One of these is the dot with a line before it, which has a minus sign. And the other is a dot with a line after it. Okay? And another exercise is that this is homotopy equivalent to, okay, so BSBS is, so let's just look back at this. BSBS is BS1 plus BS minus 1. Okay? And not surprisingly, this one and this one are isomorphic, and this one and this one are isomorphic. So in fact, these maps, when you project it to the things, are actually just isomorphisms. And so whenever you have an isomorphism appearing in a complex, you can contract it out. It's a contractible summand of the complex. It's a complex which is in a summand of the other complex and is itself contractible. So this should cancel this, and this should cancel this, and what remains is him. Huzzah. Here, this guy is bs minus 1 and bs plus 1. The bs plus 1 is going to cancel one of these copies, but the bs minus 1 survives. And so you end up with a bs minus 1 going to bs plus 1 going to R2. In these homological degrees. And this map that you're left over with, once you figure things out, is this. Multiplication by CS minus. Up to scalar. Okay? So this is sort of a nastier example. Why is it nasty? Because after you sort of cross off contractible summands, you get things with weird shifts. We're in degree 0, but there's a shift by minus 1. Right? I mean, there are weird shifts involved here, but they cancel out. Whereas here, there's weird shifts that don't cancel out. That's because this is not a reduced expression. So what are these things quasi-isomorphic to? That's easy. Okay? We know that Fs is quasi-isomorphic to Rs. So Fs is quasi-isomorphic to just R.
So see that to cancel it off, you need that map to be 0.
Which map?
Bs1 to R2.
What is this map? No. This is the dot. If you put a dot on top of this, then this left multiplication and right multiplication become the same. So this double composition is 0.
Okay. So I see. So it's not either one that is.
No, it's some linear combination inside these things. That happens all the time. It's really annoying. So the point is that this is quasi-isomorphic to R. There's a quasi-isomorphism to R shifted by minus 2, I think, maybe, which maps into here by that. But this is a quasi-isomorphism, but it's not invertible. Okay? So that's what you expect, because each of these is quasi-isomorphic to Rs with a shift by minus 1. Rs into Rs is R. Let's do another example, which is also on your exercise sheet. Fs, Ft, Fs, 1m is 3. All right, so I'll just do one, and I'm going to stop drawing the maps.
When you write Rs into Rs is R, you are thinking of it as the minus.
Yes. So I'll state something in a sec. So this maps into all ways of leaving something out. So here I leave out the last term. Here I leave out the middle term. Here I leave out the first term. I'm going to stop writing the shift. Maybe I'll write the shift actually one more time. Sorry. This goes to all ways to leave out 2 terms. And this goes to all ways to leave out 3 terms. The maps are clear. The signs go follow this thing. OK? Now what happens? This thing decomposes into BSTS plus BS. This middle term decomposes into BS0 plus BS2. And it turns out that this BS0 contracts against this BS0. This BS2 contracts against that, or one of some linear combination of these BS2s. And what remains is actually really pretty. BT is actually BST. And these all have the appropriate shifts. phenomenal. This will not happen in general. You wish it was this easy. Okay? But it does happen here. And the other thing you observe is that once you cross off all the nastiness, all that's left is shifts that are correct. Right? Shifts that agree with the homological degree. How do you know that this is going to cross off with that? The point is that if you have a big complex and it's got some summands, and the map between these two summands is non-zero. In this case, we know that any non-zero map of degree 0 is an isomorphism. So if any little term inside something is an isomorphism, that means that you can cross them out, that there's some homotopic complex where they're gone. So this is a homological algebra argument that I leave to you. I think I will be repeating it in my notes in a sec, so let me just double check. When I talk about minimal complexes, yes, I'll talk about minimal complexes later. I will repeat it later. But the idea is that if you can show that the map from here, from this summand to that summand, is non-zero, and that's enough to guarantee that they'll cross off. The map might be 0. That could have happened. But it never does. Anyway, here's Rouquet's theorem, which is that these complexes, Fs and Fs inverse, give a strict categorical action of the braid group of W. I explain what that means. Okay. So we've shown that Fs, and Fs inverse are inverses to each other as far as a categorical action because we constructed this map. But in fact, we can construct a canonical such isomorphism that satisfies a bunch of relations. Okay? And so here we've looked at Fs, Ft, Fs. It's this thing. Well, this is obviously S and T. So you can switch S and T and nothing happens. Okay? So Fs, Ft, Fs is homotopy equivalent to Ft, Fs, Ft. But in fact, we can fix a canonical such homotopy equivalence such that a bunch of other relations hold. Okay? So this is a strict categorical action, which means there's a canonical way of identifying any two things, okay, in this homotopy category. Okay, which is, so said another way, these things satisfy the braid relations, and the endomorphism ring of any given Rouquier complex is actually just R. Okay, up to homotopy. Right, so that's going to be the thing that guarantees that it's canonical, because no matter how you compose them. So not only is the endomorphism R, and then you can choose scalars on everything such that it works, such that everything composes correctly. And so actually the trick that he did to show it was he showed that in the derived category you can make these maps canonical. And that's easy. And then he sort of used that to bootstrap that because you can construct the maps in the homotopy category, and they descend canonically they descend to something that composes, then they must have originally composed correctly. That was his argument. It's a little tricky. My remark is that I have a paper with Krasner, Dan Krasner, who is no longer in math, which is in type A. We explicitly construct everything. And we show a slightly stronger statement. So in type A, braids are really topological. And there are these things called braid cobordisms, which are surfaces that span these braids in 4 dimensions. And we actually showed that any braid cobordism gives a canonical homotopy equivalence. And that the braid cobordisms themselves have relations, and those relations correspond to equalities or homotopies between chain maps. So there's an action of braid cobordisms, which is a slightly spiffier and fancier 2-category than just the 2-category associated to the braid group. So if you ever want to see a ridiculous number of incredibly explicit calculations with Rouquier complexes, go look at that paper. And all the exercises will have already been done there. In gory detail. And there we use the sign convention I described here. Okay. So, we've observed that whenever Bxn appeared in two adjacent degrees, they canceled. What's with that? So here's some fun homological algebra. So let A be a local ring, or maybe a graded local ring. Okay. Inside the homotopy category of A modules, any complex is homotopy equivalent to a minimal complex. Okay, so what's a minimal complex? Write it CW min, where all differentials lie in the maximal ideal. Okay? So, the point is that if a differential is not in the maximal ideal, it's essentially an isomorphism. And you get two contractible sumends and they disappear. So again, the differential could be 0, between two things. You could have two adjacent things and the differential could be 0 and they wouldn't contract. Okay? So this is the other way of saying it. So this is the same thing as saying that there's no contractible sumends. I don't necessarily mean a complex of free modules. But you can talk about the image of a maximal ideal inside another Hahn space. That's what I mean by this. I really mean the Jacobson radical of the category, but there's all sorts of ways of saying this. Okay? And now, there's many different notions of many different minimal complexes, but any two C mins are canonically isomorphic. Oh, sorry, non-canonically. Non-canonically isomorphic, but they are isomorphic. And the proof is that anything not in the maximal ideal leads to a contractible summand. Then you contract it and you repeat until you're done. Okay? So, the exercise is that given the Zergel conjecture on all elements of W, the endomorphism ring of the direct sum of these guys, this is not an exercise anymore, is a graded local ring. All right, it has no negative degree morphisms. It has only in degree 0. It's semi-simple, consists only of identity maps. And then above that, the positive degree things are the maximal ideal. Okay? And of course, if you actually just have S less than or equal to W, then you only have to look at endomorphisms of By, Y less than or equal to W. Here it was all elements. So, you can't just assume this unless you know the Zergel conjecture for the case that we care about. Okay? But certainly, if you know the Zergel conjecture up to a certain point, you can use these arguments to deal with any complex for a reduced expression of W, for instance. Because everything that appears will be less than or equal to W. Okay, so this is sort of a nice way to deal with these complexes. So we're going to let FW, so we've talked about F underline W, which is some tensor product. So So FW is going to be F underline W min. Or what did I put min? On top or on bottom? Min. For any reduced expression. The point is that if you have two different ones, these are homotopy equivalent. And therefore, their minimal complexes are also isomorphic. Okay? But this is non-canonical. All right, it's non-canonical. For any reduced expression with all plus signs. Right? So remember that the W could have pluses and minuses because it's a braid group, but we're just taking pluses, positive braids. So you've seen many examples of these minimal complexes now. This is what I mean by a minimal Rukier complex. And sometimes I might forget, and I might just call it a Rukier complex. And maybe these don't exist, but certainly if we have the Zirkel conjecture after a certain point, then it does. Okay. So we can't deduce from this that in the minimal complex that two adjacent things die, because the map between them might be 0. Okay. Certainly the map is a scalar multiple of the identity for degree reasons, but it might be 0. Okay. Right. And if we didn't know the Zirkel conjecture, then there might be degree 0 maps that are in the maximal ideal. There might be nilpotent degree 0 maps. The Zirkel conjecture says there aren't, but theoretically they could be. So there's a bunch of exercises. I'm going to tell you that, in fact, it always cancels. Okay? I mean, that's what happens in real life. This is something called the diagonal miracle. And this is one of the things that Jordy and I have proven. But so in general, given a Rukier complex, this fact that all adjacent things cancel, then it's easy to at least find out what the size is, if not the maps. Right, once you cross things off, the maps that remain can be complicated, as in the FSFS case. But you can find sizes. There's exercises like that. So let me just get to this point where I can state this diagonal miracle. So let k less than or equal to 0 be complexes of Zirkel bimodules such that the homological degree I is some direct sum of various bx's with various shifts, but only shifts j appear for j bigger than or equal to I. Why is this less than or equal to 0 as opposed to bigger than or equal to 0? Unfortunately, that's life. I mean, we didn't make up this notation in general. Bigger than or equal to 0 are complexes such that the only shifts appearing are less than or equal to I. Okay. So, an example, FSFS, we had a shift of -1 appearing in homological degree 0. So this is in k bigger than or equal to 0 because the shift is too low. Okay. The point of the bigger than or equal to 0, less than or equal to 0 stuff is that the Zirkel conjecture implies that this is a T structure. Okay, so we haven't gotten there yet, but in fact, the Zirkel conjecture does imply that this is a T structure. You can unravel that. And the list thing goes, there's really HOMs in one direction and not in the other direction. So I can't switch these two as much as I might want to. Okay? And so most of what we've seen is in the core, which by definition is the intersection of these two things, where the homological shift is equal to the degree shift. But in fact, but FSFS, for instance, was in k bigger than or equal to 0 intersected k less than or equal to 1, whereas fs inverse, if you did that calculation, would be in k less than or equal to 0 intersected k being equal to -1. So those aren't actually in the core. But they're measurably far away from the core. So here's the exercise. If W is a positive braid, right, it has no negative signs. We're just doing fs, fs, ft, fs, fs, fs. Then fw is in k being equal to 0. We can get negative shifts, but never positive shifts. Or too negative, but not too positive. Okay? And this is an important exercise. Maybe I forgot to put it on the exercise sheet. But the hint is that when you tensor with BS, sometimes the shifts go up and sometimes the shifts go down. But any time the shift goes up, it cancels with the going to R up part. Right, so you're tensing when BS goes to R. If you tensor with some BX where XS is less, then you get BX minus 1, which is still in this, and you get BX plus 1. But then the BX plus 1 in this degree goes to the R tensor BX 1, because of the BX plus 1 in that degree. And this map is non-zero, and it cancels out. Okay? So this is how you show that whenever positive shifts appear, they die when you're tensoring with FS.
In the minimal.
In the minimal. Right. So in the original complex, there's absolutely shifts all over the place. But in the minimal complex, we have all those positive shifts cancel out. And this statement, oh yes, complexes such that the minimal complex has this. Sorry, that's very, very important. All right, you want something that's, true up to isomorphism. Absolutely. Thank you. So maybe to not assume that there's a minimal complex yet, you can say a complex is isomorphic to a complex where this is true. Okay. Theorem, which we call the diagonal miracle, is that FW, this minimal complex, is in the core. And it has BW sitting all by itself in homological degree 0. Right? So what you start with in this F underline W is the Bott-Samuelson sitting in degree 0. But everything else cancels out, and all that's left is BW. And moreover, when you cancel out everything, only shifts appear in the right place. Okay? And this is proven only assuming, well, S of y for all y less than or equal to w, which of course is everything that shows up in the original complex. Okay. So this is the diagonal miracle. And as you may have expected then, the first differential is then a map from BW to some summand of these BS I hats. And this is our replacement for sigma. This is going to be our map, which allows us to apply this proposition about how Riemann implies hard left shifts.
From this, what you say? So you're going to get a complex.
So, the first differential is some map from BS of degree 1 to some summand of BS, some direct sum of BS, W. So, okay. There's only a W here. Okay, so we're not there yet. We need BSBW and weaving out S at the end. So we're not quite there yet, but we're close enough. And this is not just any summand, it's a semi-small summand. Because all the terms have the right shift. Right? So if we call this a degree 1 map as opposed to degree 1 map, degree 0, we have to shift this back down. It becomes actually in degree 0. Moreover, what do we know about this? We know the homology of this complex. Homology of FW is precisely the standard guy shifted by minus the length of W. Yeah. Okay. He maps into BSW, sending 1 to CS1 minus, CS2 minus, CSD minus, which has the same degree as C top. Okay. So you have a complex, and its homology is actually concentrated in degree bigger than or equal to C top. That means that it's injective below that degree. Okay, it's in fact injective. The statement that's injective below degree 0 is much weaker than this. It's actually injective way almost everywhere. Okay? So this implies that it's injective below degree length of W. Which is fantastic, so now we can use it. So this is what we're eventually going to use. Okay. Now, I'm not going to prove this for you. It's a little technical. It's not so exciting. It uses some work of Williamson and Lobodinsky that basically says that there's standard filtrations everywhere, and Rouquier complexes split after taking the associated graded of these standard filtrations. So but the point is that we can prove it only using this. So that's going to be part of our induction. Okay. Let's see. Objective below degree 0. Okay. That was everything that I had here. So I guess that means I'm done. Exactly. And you can do lots of Rouquier complexes in the meantime.
Monday.